Greetings, I am Mike Grontman. This video clip illustrates orbital mechanics features of geostationary satellites. More video clips illustrating other effects of interest to space mission design and to spacecraft design can be found on the website astronauticsnow.com. The simulations are performed using AGI's STK. Geostationary satellites, or GEO satellites, are especially important for numerous applications such as communications, direct TV and radio broadcasting, data relay, navigation, and signals intelligence. The key feature of such satellites is that they appear at the same point in the sky for an observer on the ground. To appear stationary, the satellite must be in an orbit with an orbital period 1 sidereal day, or 23 hours, 56 minutes and 4 seconds. Orbit radius is 42,164 kilometers, with the satellite located 35,786 kilometers above the Earth's surface. The orbit must be circular, that is with eccentricity 0, and equatorial, that is with inclination 0. Gravitational forces of the Moon and the Sun disturb the geostationary orbit, causing change in its inclination, also known as the north-south drift. To counteract this natural effect, geostationary satellites carry propulsion systems providing velocity increments, or delta V's, about 50 meters per second per year in orbit. This satellite function is also referred to as north-south station keeping. This video illustrates effects of gravitational forces of the Moon and the Sun on a geostationary satellite. Consider now a geostationary orbit shown in white color. It is circular and equatorial with 0 eccentricity and inclination. The white vector points at the vernal equinox. The yellow vector points at the Sun. This Sun vector will complete one full rotation in 1 year. The radius of the geostationary orbit is about 6.6 times larger than the radius of the Earth. Our simulations cover 75 years to illustrate the effect. In this segment, 1 year of orbital time is compressed into 10 seconds. Each full rotation of the Sun vector corresponds to 1 year. The initial geostationary orbit is shown in white color. The red color orbit is our geostationary orbit evolving in time. One can already see that the orbital plane begins to deviate from the equatorial plane. This orbit tilt, characterized by inclination, grows approximately 1 degree each year. Inclination, or the angle between the orbital plane and the equatorial plane, grows almost linearly with time. The Moon and the Sun are not in the equatorial plane, and they exert gravitational forces with components normal to the orbital plane. One can think about an orbiting satellite as a rotating disk of a toy gyroscope, and out-of-plane forces producing torque and causing precession of the spin axis of the rotating disk. The Sun is much more massive than the Moon, but it is significantly farther away. As a result, the Moon is responsible for roughly 2/3 of the effect, while the Sun for 1/3. The Earth is not perfectly spherical. Due to centrifugal forces caused by its rotation, the Earth's diameter at the equator is slightly larger by 1/300th than the distance between the north and south poles. This Earth oblateness is characterized by the coefficient J2 in the expansion of the Earth's gravitational potential. Asymmetry in mass distribution due to oblateness of our planet causes regression of nodes of satellite orbits and rotation of their lines of apsides. Incidentally, this effect enables two common satellite orbits, sun-synchronous orbits and Molniya or Molniya orbits. In this first segment of simulations, we covered approximately 14 years. With current inclination about 10 degrees, one can easily notice the motion of the points of intersection of the red and white orbits. This is regression of nodes caused by the Earth oblateness. These 2 points are known as the ascending node and the descending node, and the line connecting them, shown as the dash orange line, is the line of nodes. The line of nodes crosses the center of the Earth and rotates in the equatorial plane. The regression of nodes is caused by ablateness of the Earth. We continue now to follow the evolution of our geostationary orbit for additional 60 years. The simulation rate will increase in the beginning of this segment. Each year will be compressed into 2.5 seconds only. One would later see that orbit inclination achieves maximum of about 15 degrees and then begins to decrease. The orbital plane would then reach back to the equatorial plane in roughly 55 years and then increases again. All this time, the line of nodes continues to rotate. Geostationary satellites also experience drift in longitudinal or east-west direction. This drift is also caused by asymmetry in mass distribution of our planet. Not only the Earth is oblate, but it is also non-uniformly oblate at different geographical longitudes. This particular asymmetry is described by a coefficient J22 in the expansion of the Earth's gravitational potential. The east-west drift, as it is known, can be counteracted by velocity increments of about 1.5 meters per second each year. This is much smaller than the required velocity increment capability of 50 meters per second per year for counteracting the north-south drift. If not controlled longitudinally, geostationary satellites would periodically move in the east-west direction, as observed from the Earth, over 2 stable points. One such point is in the middle of the Indian Ocean. The second stable point is roughly at longitude of Colorado. On a historical note, Hughes Aircraft designed and successfully deployed first geostationary satellites in the early 1960s for communication purposes, beginning with the live transmission of the Olympic Games in Tokyo. As you have seen, our geostationary orbit plane has reached back the equatorial plane and is now increasing inclination again. Such quasi-periodic change in orbit inclination with a period of roughly 55 years is typical for geostationary satellites. The final figure in this video shows a graph of inclination change with time illustrating this quasi-periodic motion. Note that the lifetime of realistic geostationary satellites doesn't exceed 10-15 years, so after deployment, satellites experience increase in inclination and never reach the decreasing phase while operational. Therefore, the essentially quasi-periodic north-south drift is often referred to as unidirectional for operational purposes. More video clips illustrating other effects of interest to space mission design and to spacecraft design can be found on the website astronauticsnow.com. Thank you for watching. I'm Mike Grontwan.